Right. So I wanted to talk through the write-up that I have for number one, since it is fairly computationally difficult, and I began to use a notation that I didn't um, mention in my lectures. So for number one, right, we have this problem. We have a curve, and we're supposed to calculate the tangent vector, the normal vector, the binormal vector, and the curvature for this vector function. And on the formula sheet, we had these formulas. These are the ones that will be relevant for us. Now, for the curvature, actually, it turns out that this other guy might be a bit more useful, especially if you don't trust your previous calculations, which for this problem is a rather sensible thing to do. But there are two different ways you can calculate curvature, and we'll see that last. Um, okay. So for the tangent vector, well, we have to calculate r prime and then its magnitude and divide by its magnitude. And this is already where there's an algebraic thing that if you notice it, it makes your life a whole lot easier. And if you don't notice it, well, then the computation becomes pretty uh, uh, terrible. So when you square each of these components and then put them in the square root, the thing that is really convenient to notice is that this is actually a perfect square trinomial. This is actually this quantity, e to the x, or e to the t plus e to the minus t quantity squared. This too ends up being the middle term. See, you can imagine expanding this out, foiling this out, and you'll get this inside quantity. So that allows the square root to disappear, which is really convenient, especially because we'll have to take a derivative later on. And if you want to take a derivative with a square root involved, well, there's a lot in there. Okay, so there we have the magnitude of r prime. We can then divide by it in order to get the tangent vector. Okay, oh, from that, so this is also another stage where you might um, make your life a whole lot more complicated if you didn't take the derivative in the straightforward way of just using quotient rule three times. So for me, when I first encountered this problem, I made it too complicated for myself. I try to get rid of I tried to avoid using quotient rule initially, and so the way that I had first tried doing this was I tried to get rid of the expression in the numerator, which amounted to multiplying the for this fraction, it would be I multiplied like the top and bottom by e to the minus t to make the numerator 1, and then I multiplied the top here for by e to the t in order to make it 1 or minus 1. And then you can do that, and you can get away from doing quotient rule because so let's take the second component function. So if we were to have multiplied top and bottom by e to the minus t, we would end up with uh, this quantity, e to the minus t, and then you could distribute that in, which will make looking at this a little bit more easy. So you end up with this expression, and with the other one, it gives you something similar. So I believe it'll be e to the 2t plus 1 with a minus in front. So you could rewrite and end up with these for the two functions. The problem is that as you continue going through the work, you end up having to reshuffle things around just in order to make the calculation work. So like by doing this one step here, we avoided using quotient rule, but the difficulty increased from all the subsequent steps that required us to basically renormalize things, constantly multiplying by e to the t and e to the minus t to get like the denominators to be the same so we can simplify stuff, and it ends up being a mess. So it ends up being a mess just because we try to avoid using quotient rule. So it turns out actually it's a whole lot easier if we just bite the bullet, do quotient rule up front for each of these three component functions. And that isn't too bad. So For this one, I think it's pretty. I think you can kind of tell just by looking at it that this is what you get. So when you do quotient rule, let me maybe erase this. Up, it's not working quite as well. Okay, so when you end up doing quotient rule with this, I'm using the version that I use is gf prime minus fg prime over g squared. So the only difference between what I do and what a textbook does is I swap the first two factors. So when you think about it like this, this term goes to 0 in the quotient rule. So you end up with just minus of the numerator times the derivative of the denominator, which gives you this. So you can get that first term right away. With these two, there's some simplification that occurs with the quotient rule, which I didn't write here, but I guess I may as well explain it now. So when we take let's just focus in on the second guy. So if I use the quotient rule on the second guy, it'll be denominator times derivative of the numerator minus numerator times the derivative of the denominator minus t all over the denominator squared. So and then the simplification we can get is, let me see, yes, this guy and this guy cancel. These both give you e to the t, but with opposite sign, or e to the 2t. So the first guy gives you e to the 2t, the second guy gives you minus e to the 2t. And then the two that I didn't cancel, notice that I get an e to the, I get 1. These two multiply together to give 1. These two multiply together also to give 1 because of the signs. So we end up with a 2 on top, which is exactly what I've written here. And the same kind of cancellation happens with the taking the quotient rule on the third component function. So we end up with this. Okay, so that's rather nice. Now let's talk about the magnitude of this, because we need to divide by the magnitude to get the normal vector. So, well, we square each of these guys, and the convenient thing about the answer being written in this way is that the denominators are all going to be the same when we square. And so we can immediately combine all of these fractions together. And the numerator, we're combining as such. So, yeah, the minus gets squared away. The root 2 becomes 2. This term becomes this. This factor becomes this factor squared. And then 2 squared plus 2 squared is 4 plus 4, which is 8. Okay. And here we have another algebraic nicety that happens, which is a bit unexpected. When you expand this guy out, I guess even before that, I factor out a 2 from the numerator. So that gets rid of this 2 here, and that turns this 8 into a 4, and we end up with the root 2 sticking around outside of the big radical. Okay, right, after that, then you expand this guy out, and you end up with this quantity. And then notice what the 4 does to this middle term. It turns a minus into a plus, which means that we end up with the positive version of the perfect square. We go from this with the minus in the middle into this part with the plus. That's what this plus 4 does to this middle term. So it's kind of the nice flip-flop that happens with, I don't know what to call this, but it's a pattern that you often see. So once you see it, you kind of are more able to spot this kind of this algebraic trick that happens. Okay, so now that we have this, well, it's pretty easy to take the square root of it. Notice that these two factors are the same. So the powers cancel, so you end up with a copy of it in the denominator, raised to the second power. Then you take the square root of that, which just gives you the expression e to the t plus e to the negative t in the denominator, which is just this. Okay, and so that is the magnitude. It's really clean, actually. And lastly, you want to divide this through every one of these functions. So notice that, um, well, with these two guys, you end up with a square root on top because you have 2 divided by root 2, just gives you root 2. And then you end up with this quantity in the numerator, which cancels one of the copies in the denominator. So you just get one copy left over in the denominator. With this last guy, or with this first guy, I should say, the square roots both cancel. This guy doesn't cancel. The Because notice it's a plus, not a minus. So the plus variant will cancel with the denominator. Well, it'll cancel one copy in the denominator. So you end up with this expression. And again, avoid doing anything algebraically to it. Just leave it as it is written. Okay. From there, binormal vector. So this is where I'm using a slightly different notation for cross products and for vectors, just because I wanted to save space in the write-up. So what I'm doing here is I'm writing a vector in column form instead of this row form that we're more used to seeing. So um, the way you read this is that the first guy is the x component, second guy is the y component, third guy is the z component. Right, so this is a vector written as a, well, in classes like linear algebra, this would be called a column vector, and things like this would be more called like a row vector, but they would still have square brackets around them. It's kind of to allude to the fact that column vectors and row vectors are basically matrices, or you can think of them as matrices. So anyway, the one advantage of writing it in this way, and let me just confirm with you guys that this is t and this is n. If you kind of scroll back up and kind of compare, you can see that t was copied down here vertically, and so was n. Right. So one thing we can do, actually, this is another way of visualizing the process of taking a cross product. So you're used to having I, J, and K as being like a top row. Well, now that we've written it like this, it's as though we've transposed our matrix. It's as though we've reflected things about a diagonal. So you might have, reflecting it about this diagonal, you would end up getting I, J, and K up on top. Because we've reflected it already, it is as though we can have I, J, and K over here. And so then we can do our computations mentally without writing I, J, and K, right? So if we try to calculate the component, the x component, we would cancel these two guys, and we'd have this submatrix. Let me get rid of the diagonal part. We would have this submatrix. You'd multiply these two, and then subtract off the anti-diagonal. And if you do that, let's see. This times this is, I think there's some simplification here that happens. Root 2 e to the t plus root 2 e to the minus t all over e to the t plus e to the minus t quantity squared for the first term. And then notice that if we factor out a root 2, we get a cancellation with the denominator. Yeah, e to the t plus e to the minus t quantity squared, which does indeed give us this first component function. If we instead focus on the j, right? So then it would be this times this minus this times this. I think this one I didn't do anything clever. I just wrote it straight up here. Oh, the minus here is because of the sign alternation. So there's a negative there. And then root 2 times root 2 is 2. And then you minus, let's see. How am I doing this? Okay, I think that because this is the anti-diagonal, the negative will cancel with this negative here. But then I have this negative in the numerator and this negative, and this in the numerator, and that combines to give me this quantity. Yeah, that's what I'm doing. And then of course the denominators combine together. And lastly, for the k, the k, we have this submatrix. We have 2 on top, and then we have this with a minus. So for the anti-diagonal, the minus will cancel with the negative here, and you're left with this e to the t times this quantity, which gives you this quantity. Yeah. And so that's how we end up with this guy. And then, of course, what we want to do is simplify the numerators, which I do as my next step. Let's see, is that clear? Yeah, there's a bit of mental math going on here. So the e to the minus t times e to the t gives you a 1. So you have 2 minus 1 plus e to the negative t times 2, which gives you this. Yeah. So yeah, there's a 1 here that cancels with the 2. And the same thing should happen here. This e to the t times this e to the minus t gives you a minus 1. So you get 2 minus 1 and then plus e to the 2t. That should be a plus. I think that's a typo. Yeah, I think that's a typo. That should be a plus. I'll fix that before I upload the PDF. Okay. Yeah, because I do fix it here. The next thing I do is I notice that I can simplify the expression a little bit further, and this is not necessary, but I did it because it looks a bit nicer. So this is where we can use this algebraic step of if I multiply top and bottom by something nice, I will be able to get rid of a copy in the denominator. So in particular, if I multiply, here's a different color. If I multiply top and bottom of this by e to the t here, you see that's where this e to the t comes from. When we do this when we distribute this, we get e to the t plus e to the minus t, which is going to cancel with a copy in the denominator. That's why we get this. For this term, this is supposed to be a plus, which means we should multiply by e to the minus t on top and bottom, which is why we get a e to the minus t on this guy. And so after you distribute, yeah, you get an e to the t plus e to the minus t, which cancels with a copy in the denominator, which gives you exactly that. And so that's how you can compute the binomial vector in not too terrible of a manner, but it all required that you had a really convenient expression for probably for both the tangent vector and the normal vector. I definitely saw people write extremely complicated expressions, but this is the cleanest way that you could write these answers, I think. I'd be surprised if there's any cleaner way of doing this. Okay, and lastly, curvature. So supposing that you didn't trust your calculations for the normal vector and tangent vector, then you could just use, as stated above, you could just use this expression using the first derivative cross the second derivative, take its magnitude, and divide by first derivative magnitude squared, or cubed. Okay, so that's nice because the two derivatives are pretty easy to compute, since these are exponential functions. Next, you can take the cross product, and I'm again writing it in this fashion just to save a bit of space. So let's just talk through it again, just to make sure that everyone follows. So in order to compute the first term, we have this submatrix with this main diagonal and this antidiagonal. So you get 1 from this main diagonal minus, and then negative 1 from the antidiagonal, which gives you that expression, which simplifies to 2. For the second component, we have these two um, diagonals. I don't know what to call them. So the main diagonal is root 2 times e to the minus t. The antidiagonal ends up being 0 because of the 0. And so you end up with this expression. The negative is coming from the sign alternation. And then for the last component, you have this submatrix. Main diagonal is 2 times e to the t. Antidiagonal has a 0, so you just end up with that expression. And then you can clean that up a little bit. From there, we want to take the magnitude in order to fit it into the expression that we're trying to calculate. So computing the magnitude, again, yeah, so after squaring everything, you pull out a factor of 2, you end up with this expression, and then the key simplification here would be noticing this is a perfect square trinomial. This is just e to the t plus e to the minus t quantity squared that is inside of your square root. So you can cancel the square root, which just gives you this quantity there. Okay, and then lastly, we have the magnitude here. And so the magnitude is again, it's the same thing, right? Um, after we square each of the components, we get this. This is the perfect square trinomial. You get this expression. The square root and square cancel. You end up with this. And then feeding everything into the formula for the curvature, you got a nice cancellation there. So that is pretty decent if you are able to do it this way. Alternatively, if you did get T prime and R prime and you actually trusted your results, especially if you got them in such a clean manner, then you could just multiply across basically. I had to reciprocate the R prime. You can check that R prime was that quantity itself. R prime magnitude was that. And T prime magnitude, I think I wrote it up here somewhere. These would be expressions that you would have already computed in your work. So, and you can see that they agree. So that's pretty good. All right.